Jay, wait, do you put vector arrows?
Yeah.
You know us.
And then
You know us.
You know us.
Mm-hmm.
Dot product 13. I do know you. 13. All right. Number 54.
Oh, 54 not. Yeah.
Neither. Wait a minute. We talked about orthogonal yesterday, but what's going on with parallel? No clue? Alright. Parallel, long story short. One vector is a scalar multiple of another vector. One vector is one scalar multiple of another vector. What do I mean? If we were to, let's see if we get this out. Okay. If we were to graph -1, 5. True?
Yeah.
-1 and then positive 5. 1, 2, 3. Okay. There he is. What would it take for a vector to be parallel to?
Same slope.
Same slope or similar triangle, true? So we need to have a proportional rise over run to get to him. Okay? So when we graph the guy 3, 15, which will be 1 and a 2 and a 3 and a struggle, there's a 5, and then there's a 10, and then there's a 15. Okay. So we see this guy. First of all, if you just grab them, question kiddos, are those parallel? No way, Jose. Okay, ignore what I just did. It's a little bit rough. But okay, this way. They're not parallel. This guy, not parallel. I know, the judgment, I can take it. So, not parallel, right? Okay, so since they're not parallel, that's all well and good, but my question is, what would have made him parallel? If he's not, whatever, parallel, question. I'm done. Who would be a parallel guy to this first one, which was that's okay. Who would be someone that's parallel? I think we've been
How about
talking about
-3 and -15?
that one.
No, -15 and 15.
Because what would that really change? Well, instead of going positive 3, it would go negative 3, and then it'd go 5, then it'd go 10, then it'd go 15.
If they wouldn't be parallel, then we could see those.
It's still the same.
No, they're not be parallel, you see. Because they would go through -1 and 5, then -2 and 10, and then -3 and 15.
Oh, because they
So
would
they
be.
cannot be parallel.
They can't?
No, they're gonna be like on each other.
Oh, what is that?
It's that.
It's the same.
It's neither.
It's not orthogonal.
Oh, okay.
There's 5, there's 10, there's 15, so it's a little smaller, so I feel it. There's -1, there's -2, there's -3. Okay, so the first one has the point at -1, 5, right?
Yeah,
The second one has the point at -3, 15, right?
yeah.
Okay, so one guy goes here, and the other guy goes where?
So top of it is continuous.
On top of it and continues, if I did it correctly. They're not parallel, they intersect unless you remember, hold on, wait a minute. Vectors, do they have to stay in one place? Oh, which means I can move him?
Yes.
Oh, and if I move him, what's true?
They're parallel.
They are parallel. So even though they do go on top of each other in the sense of right here, vectors can be moved. So we're not going to use the traditional sense of parallel can't intersect. We're going to say, hey, do they have the same direction and proportional magnitude? AKA, are they similar triangles? AKA, are they parallel vectors? So, answer is, if one is a scalar multiple of another, hey, what does it take to go from him to him? Multiplying the horizontal and vertical by 3. Cool. What would be another parallel vector to both these guys? Yes, you guys show your vector arrows. -420 is green or right? -420. Appropriate. All right. So, question: is it parallel? Yes or no?
Wait, so let me stop and open though.
Is it parallel?
Everything.
Yeah, but you don't even have to do a picture. Who cares? Look at the math. Why would you multiply -1, 5 to get -420? Yeah, times a scalar of 4. So we can say this guy is 4 times that guy, this guy is 3 times that guy. As long as we can say that one vector is a scalar times another vector, they are parallel. But since these ones weren't, they were going 2 different directions, they were not, since the dot product was not 0, they were not combined. Are we okay?
Yeah, we're good.
We're holding on.
Hold on, alright. Let me change that, let me change this. Okay, number 76. Music man. Music man. It's a classic musical that has to do with a lot of things, but one song is 76 times. 76 always makes me think of it. You guys corresponding to mine is more innocent. Alright, so force due to gravity. Check unit vector check using a formula. Projection check using a formula. My stylus. Okay, I got it. Final answer 5,318 times. But they also give things in between, like the magnitude of the force, which means we need equal force to keep the vehicle from rolling down the hill, and then the force perpendicular to the hill was the last answer. Oh, because this is an incline of 10 degrees, right? Yeah. Which is not much of an incline. If we think unit vector has length of 1, right? We're just going to put in there for sake of argument. How do we find the A and B of any vector? If we know the unit vector, or if we're trying to find a unit vector, the hypotenuse is 1. If we know the incline, that's 10 degrees. So we can use our magnitude, our magnitude cosine theta for A and our magnitude sine theta for B. So they went ahead and did 1 times cosine 10 and 1 times sine 20. That makes sense. I think that was from section 6. Yeah, only because they say that. Alright, kiddos. Any questions on any of the odds? Okay. Oh, we're okay. Never mind. Alright, let's get out of here. Section 6.5. See, 6.4 wasn't bad. 6.3 was bad because it was all the intro to vectors. 6.4 was just a little bit further application.
What's 6.5?
6.5? Let's check it out.
That's fine.
Height.
Complex numbers. This is random or maybe not.
Fine.
Trigonometric form of complex number. A little bigger. Trigonometric form of a complex number. Yes, happy Tuesday. Have a week where Fridays and then weekend. Then we have a 3-day weekend coming up sometime. Make sure we're multitasking, but I don't mind you guys getting set up. 6.5, we return to complex numbers. It doesn't correspond. And I'll show you why as you guys are chilling and writing notes. How does this relate to what we've been doing? complex number can be graphed, if you think about the x-axis as real numbers and a y-axis as imaginary numbers. So then the real component is measured on the x. The imaginary component is measured on the y. Now that triangle is just something that I can kind of add technically, I guess, we would just add a different one. Normally we also see a legal line. And what is that the graph of? This little guy, right? 3 minus 2i. Remember, negative numbers have applications, electrical currents, things like that. We haven't really applied them, it's kind of outside our scope of just introducing future math, but if you're curious, it would be something very interesting to apply. Why complex numbers? Why imaginary numbers? It seems silly. Oh, it's like this. So what's going on? Can I scroll down just a little bit? What's going on with the absolute value? Is it really absolute value? Like make it positive? What is that absolute value notation for? You guys already written it? Distance. Where have we seen a notation that stands for distance? In vectors, what was it called? Magnitude, right? And how do we show magnitude? With double lines. Okay, so with complex numbers, I know it's a little bit annoying, but the notation changes a little bit. It's just single lines. So when you see absolute value of a complex number, it's not actually talking about just make everything positive. It's talking about the distance, which we know because of vectors. Oh, that's just a squared plus b squared square root. Pythagorean theorem. Because a and b are just horizontal components, right? So then in number 6, when it says plot the complex number, then question, kiddos. Where are we putting the 5? On the x or on the y? On the x because it's the real component, so we're going to go out 5, and then we're going to go down and y down. It's negative. Go ahead and graph our point. And how do we find the absolute value of 5 minus 12i? Sorry, I don't have that. No, it's my fault. Okay, go ahead. Start again. What would it be? 5 squared plus? Ends up being, anybody know? So 5, 12, 13. Good. 25 plus 144 is 169, and 169 square root is? That wasn't too bad. You want to think of it as kind of another further application of triangles of graph interpretation. And some of the math's going to look a lot like vector, if that makes sense. A couple more seconds until we switch. Alright, we good? Ready, set, and repeat, go. Oh man. What's going on here? Complex numbers in trig form. Wait. Standard form. We already got this one down, kind of, sort of, in another chapter. So what's going on with trig form? Aw, hold on. Look at this guy. Trig form. Be the same thing as r cosine theta plus r sine theta times I. Why should that be familiar to us after our work with predators. From a right triangle, we can pull out the relationships between both quantities, and in this section applied, A is the real component of a standard number, of a complex number, B is the imaginary component. And we can say, hey, to get A, can't we set up little relationships like sine of theta equals opposite over adjacent, cosine of theta equals adjacent over, let's see that. Sine of theta equals opposite over hypotenuse, cosine of theta equals adjacent over hypotenuse. And can't we use both of these to say, hey, what do we want to solve for A or solve for B? We have a little sine cosine formula that says we multiply R on the other side. A is adjacent, so he's going to go with cosine. B is opposite, so he's going to go with sine. And in vectors, didn't we have something like the horizontal component was equal to the magnitude times cosine, and the vertical component was equal to magnitude times sine? That's why these formulas should be. We used them in component form, now we're using them in complex numbers. R, we can say, well, that's easy, that's exactly in here. You have A and B, and no big deal. We already talked about. And then beta, that's not too bad either. Because we have opposite and adjacent. We can just use tangent inverse to solve. So even though this formula does look new, and it does, I totally agree. Z just stands for a complex number. The math is actually not in the it's just the view. So as you get to the example down below, it says, hey, here's a complex number, graph them, and write them in trig form. Okay. Graph them, what quadrant is he in, kiddos? Why? Because the A is positive, which means go to the right one. B is negative, which means go down root 3. We have our point. Then write the trig form. Hold on. The trig form. Z equals. How do we get the first part? Oh, see. I need R cosine theta and R sine theta, but that we don't have any of that, do we? No, before we can do trig form, what do we have to find first? That pieces. So R is going to equal the square root, right? Of 1 squared plus what's negative root 3 squared? Root 3 squared is just 3. Well, root 3 is 4, square root is 2. Okay. Well, let's find an angle. Tangent inverse of B over A, so I have my negative root 3 over 1. A, that's the principal, right? Focus. What angle has an opposite of root 3 and an adjacent of 1? Yeah, you need to have an opposite that's longer, adjacent that's shorter. 30 degrees would be switched, 45 degrees they'd be equal, right? So at 60 degrees, which is the same thing as a degrees. Sure, why not? So now it's 60. Wait a minute, is this actually 60? You either do negative 60 or what's another way of talking about it? 300 degrees. So we could say Z is equal to 2 times cosine of 300 plus I sine of 300. Why do you think they put the I in front, even though normally in stories don't put the I at the end of that sentence? Why put the I in front? Yeah. If you put the I after the sign, it gets kind of confusing. You might get the I. It keeps it separate. How I'd have liked to put a number if it was like root 3 times 2 would be 2 root 3 the other one. Same thing back. Go back, hold up. There we go. Trig form. Done. So we can go from standard form to trig form, but we can also go backwards. It does have to go from trig form back to standard form. Yeah, pull it apart, sounds good to me. Where's 135? Yeah, I cheated, I should. 45 degrees in the second quadrant, right? So first of all, can't we just multiply the 5 in? Then can't we say, hold on, 135, we should try to know them? Right?
No.
135 is a 45 degree, that means we get a root 2 over 2 and root 2 over 2. What's the sign of my x, of my cosine? Positive or negative?
Positive.
Negative.
Sine is positive.
Sine is positive, the sign of cosine is negative, right? So we have the negative and then we have the positive. Positive. So we plug in 5x, negative root 2 over 2, plus 5x, positive root 2 over 2, times 5. We end up with negative 5 root 2 over 2, plus 5 root 2 over 2. How can you double check that you've gotten the right one? If we go negative to somebody and positive to somebody, we're going to end up with the approximate equal value. Well, negative x and positive y would end up in the second quadrant. I just kind of double checking that. So what are we doing? Still applying trigonometry. Sorry, there it is. Just applying trigonometry. The first one we have to actually use formulas when we go from standard to trig. We have to use formulas. But trig to standard, well, don't we just kind of solve? If it was non-right triangle, where would you be going to solve? You could just use calculator, right? Like, what if it was 140 degrees? That's not good. We have to plug into our calculator and get an answer to this. Right? Okay, so, what else is there? Operations. Steve, you can do stuff with complex numbers? You can multiply, you can divide, and you can raise to a power, and then we're done. You can multiply, you can divide, you can raise to a power, and then we're done.
Is this homework tonight?
Just
Curious.
I'll look it down. You multiply, you can divide, you can raise to a power. Now, this might be an appropriate time for you. Thursday's test. Okay. You're going to have a calculator. You're going to have your homework ready in the room.
like we
What? Where am I getting to? Better study. Okay then. Just kidding. You are allowed to make a 3x5 card. One. Wait. Only the formulas 6, 3, and beyond. Log signs, log cosines, and the two areas area formulas from 6.1, 6.2 you are not allowed to provide. But any vector or complex number formulas from 6.3, 6.4, or 6.5 you can put in the formula card. If you don't bring it, you can't use it. You can't get access to that distance. So, very good. I would make myself a card because I can use it on my homework and I can use it on the test review. Yeah. But what formulas do you have to memorize? Lot of sines, lot of cosines, two area formulas.
Oh,
You're asking me. Hey kiddos.
Good.
Look at your shirt.
No, don't do that.
The class version has you stand up.
If you're standing, then you gotta go push up if you're sitting, and then get up and go.
Anyway, wow.
yeah. What? Yeah.
Okay, product and quotient formulas. You guys see similarities. You multiply two complex numbers. What do you do to their r's? Multiply. What do you do to their thetas? Add. You divide two complex numbers. What do you do to their r's? What do you do to their thetas? They kind of fit together, huh? Like if you had to memorize, it wouldn't be that awful. But you the longest, not the longest.
Oh, it's not the
It's
one.
like half hour.
Okay, that's fine.
Okay, let's come back.
So tomorrow we're just doing this.
All right, so number 45. Is it a times or is it a divide? Times. Therefore, what do you do to the r's? You times them. What do you do to the thetas? Add them. Wait a minute. What's pi over 4 plus pi over 4? Oh, come on, don't be scared of fractions. Fractions are friends. 3 pi plus 1 pi is 4 pi. 4 pi over 12 is pi over 4. You guys agree?
Yes.
Right? 3 pi plus 1 pi is 4 pi. 4 pi over 12 is pi over 4.
Whoa. Are you distributing it?
Well, let's check it. Leave the result in trig form. Ha!
Is it distributing it?
Why am I not? It says leave it in trig form, which is r cosine theta plus I sin theta stop. If they said standard form, would you keep going?
Yes.
Yes. But since
Oh,
they
you-
said trig form, we'll get to stop.
Usually real number with a number very complex.
Does that make sense?
Yes.
So, Z1 times Z2 in this example is 12 cosine pi over 3 plus I sin pi over 3. Easier Z1. Easier Z2. That formula wasn't hard, right? How about the next one? Divisions, what do we do with the r's? Triangle. Cosine of the triangle. Divide the r's, subtract the thetas. Oh, got it. I sine of 2.2. Let's leave in trig form, that's done. Is that it? For these two. Okay, hold on. Wait, what are we doing? What are we doing? Aren't we plugging in? If we multiply the r's and then add the thetas, and then we're done. If we divide the r's and subtract the thetas, then we're done. So down below, they were next to each other, which indicates multiplication. So 2 times 6 is 12. Pi over 4 plus pi over 12 is? We did it off to the side. Hence how we got pi over 4. Nicole, you got the ketchup over. Fine. You see I'm just plugging and dug into the formula? So, those two formulas, not too bad. Will it get any worse? We multiply, we divide, and we raise a power. Raise to a power. Wait, guys! Hold on. There's a guy's name, Wallace. Wait, who takes French? How would you say it?
It's how you said it.
Say one more time, strong.
It's fine.
Wow, the pressure. What else is in French?
Just
You wanna say? Are you really?
Alex, Sean, and Olani at the end of class go see Senora. Probably like a college something. I don't know. Kendrick. Sorry.
I was about to say, like, no, I ain't
Sorry,
gonna
so okay. Senora.
I was like,
communicate. So that would be like how flashbacks to
You're Kendrick. Okay. Shush. Question. Does this formula look that different than the other ones? Raised to a power, what do you do to R? Raised to a power, what do you do to theta? Now, why do I have this whole blank example thing up above? Okay, walk it. And there is a formula to do the one up above, but why haven't I wonder if maybe we can figure out the formula for ourselves.
Let's go.
What happens if we clear something? We multiply him by himself, right? How do you multiply 2 times? So what's our cosine and our cosine? What's the outer and the inner?
we're getting pretty fancy.
Oh wait, there's 2 of them, right? How are we doing? Multiplying or foiling. We have first, outer, inner, and now it's time for last. I get squared. Because remember, I is equal to the square root of -1. If you square that, you square that, and that ends up equal. So, can I change him to be -1? Right? Okay, so I'm going to have R. Well, wait, doesn't everybody have an R squared?
Yeah.
Then I'm going to have, let's combine these two, at least write them next to each other. So we're going to have cosine squared minus sine squared. Then let's go ahead and combine these two because they're the same thing. So we're going to have plus 2 cosine sine, that would be awkward, times I. I guess we could put the I in front, because that was nice with the I in front.
Yes.
I squared to me. Yeah. Wait, how on earth are we with a formula? What's going on? Hold on. Cosine squared minus sine. Who's 2 sine cosine or 2 cosine sine? Need a double angle of sine. So that's it. In order to do understand, so that can see below. To raise a complex number to a power, we raise an r to the power. And then we say the cosine multiply the angle by the power plus I sine multiply that equal by the power. And so that's 1. formulas for double angle. They started using people to the fourth power to get a little velocity. With this one, we actually have these formulas from last chapter. That's the double angle of cosine, that's the double angle of sine. So we were able to kind of check there. So maybe I forgot. There we go. Nice thing is, I'm going to make you figure out where the formula came from. I was just trying to demonstrate it. We get to use the formula once we have it. So kiddos, how do we do the formula down the road? How do we use the formula for number 7? Okay, so we raise the 3 plus the power word, trying to figure the entire number 2. So you raise the 3 to the 4th power. The radius, the outside part, just does whatever the operation is. But then the angle, 3 cosine of 4 times 60 plus I sine of 4 times 60. Now Luca, this is your question a second ago. Can you read those directions for me? Can I stop? Why not? Okay, so this is one where we are going to distribute. We are going to keep going. It says standard form, which means we want to end in something that looks like A plus BI. We don't want to keep those nasty signs and those signs. Yeah, 3 to the 4th is 81, so it's 9 times 9. We're going to have 81 times cosine of 240 plus 81 times sine of 240 times I. Now 240, hold on, easy in the circle, right? What quadrant is 240 in? Yeah, so we go 180 and 60 degrees more. Down here we have the cosine of, make it into 1/2. We have the sine of, so you're plugging our cosine, plugging our sine. We end up with negative, that's gross, 81/2, so be a decimal like what, 40.5? Minus 81 rad 3 all over 2 times 1. Got it.
I like the way we keep you with it.
Very fast.
We're done.
So wait, that's it?
Yes!
Oh, no, that's a review. It's a review.
Okay, well, it kind of sucks.
No,
We
no.
were thinking like exponents. We all knew
Pointless,
that.
pointless, pointless, pointless.
Just write this guy down.
Oh.
Oh, amen.
But isn't our root just a comma?
Yeah.
Oh. Fractional root. I see the angle being divided by everything. Now hold on, something else. Take away the K. Just for sake of simplicity. If we have a Z who's being nth rooted, another way of saying it is Z to the 1 over nth power. Same thing. You know that. Take an algebra teacher. These are the same thing, right? Okay. Then I'm going to take the nth root of R and I'm going to divide the angle by n. Oh, isn't that the same thing as multiplying by 1 over n? Oh, so it works like trick is gonna have more answers than the last one. You're gonna have more answers than the last one. So whenever you have a root which can be seen as a fractional power, it behaves the same as the logger's theorem, except you basically, by cutting the angle down, you also cut down the coterminals, which means between 0 and 360 or between 0 and 2 pi, all of a sudden you have more answers than you did before. That's kind of what's going on. You guys have kind of seen this with multiple angles when you had cosine 2x equals something like 0. You would have solved for when cosine is 0 divided by 2, you might have had 2 answers instead of 1. So let me go ahead and show you how this guy works. On an example. Q root. Alright, let's set this guy equal to z. I want the cubed root of z. It's the same thing as z to the 1/3 power, which means I cube root the r. What do I do to the angles? Wait a minute, hold on. What form is this guy written in? Cheaters! It's in standard form. What do I need it in to do my little theorem? Oh, I need trigonometric form. So wouldn't I have to start by?
No. Well, you have to.
Can I cheat just a little bit? You guys okay with that? If I go over 1 and I go up root 3, is that somebody I should know? What angle is that? Oh. So I can go ahead and say, hey, this is just, we had to kind of do a little bit of mathematical gymnastics, but now we have cosine of 60 plus I sine of 60. We were able to cheat and just kind of graph and then figure out that 60-degree angle. Now I can say, okay, cube root of z is equal to z to the 1/3. My cube root, my negative 125 over 2. And the theorem tells me cube root the r, and what do you do to the theta? But I'm not adding 2 pi because do you guys see how I did 60, so I'm doing degrees. So I'm going to do 360 instead. K is, according to the last page, start at 0 and count up. And you should have as many answers as the root that you're finding. Wait, what kind of root are we finding? So we should have 3 answers. So how do we do this? Well, you go ahead and say, alright, if K is, start at 0, 1, 2, 3. Those are the only K's we're going to use. And then I plug in everything. So we're going to end up with z to the 1/3. Cube root of 125 is negative 5 over cube root of 2. That's gross. Times cosine of 60 over 3 is 20. Negative 5 over cube root of 2. Cosine of 60 plus 360. 420, and 420 divided by 3 is 120. I'm going to do plus dot dot dot. And then what would our last angle be? 60 plus 2, 360, 60 plus 7, 27, 87, 80 divided by 3 would be? 260. My hands on finish it up.
Let's go, John.
Oh, yeah.
Right?
My hand's tired.
You put up tomorrow.
I was figuring for more keys, so maybe next time.
Kendricks.
Yeah, so you were Kendrick up in the library. Alex, Sean,
I need help. I don't know how to do math.
Gosh, what? You get the pictures here.
my test questions though. They told me yesterday, I was like, if I was there, I would just chill. Cause he was like, apparently he asked Joyce, and then he like Joyce photo was on the shot about your age.